the really big topic for differential calculus, the biggest topic. This is, so really a lot of what we do for the rest of the year is just revolves around this idea of curve sketching and optimization, right? So in order to dive into that though, we gotta learn about some concepts, some vocabulary, and then we'll just kind of build up. So we're gonna focus on extrema today. That's the topic of the day. So what are extrema? There's a bunch of different types. We can talk about them in different ways, but extrema are just extreme values, right? Really high values or really low values on a function. So this is kind of the textbook definition, and we'll get a little more informal with it. So let f be some function defined on an interval I. What's that mean? What are we even talking about there? Let f be defined on an interval I. What's an interval I? What does that mean to you? You guys got to get used to reading textbooks a little bit. Get used to this language before you go to college. An interval of what? Of what kinds of values?
Integers.
No, not integers, but okay, on a number line. So are we talking about input or output values probably? Input. Yeah, we're talking about, like, typically it would be x values. Right? If we're looking in the xy plane, for example, at the graph of a function, this would be an interval of x values. Okay? So there's some interval of x values containing some specific value c, and if the function is defined on that interval, then we would say that f of c is a minimum of our function on this interval if f of c is less than or equal to f of x for all x in the interval. In other words, c is the value that makes our function the lowest, or at least there's no other point that's lower than that. Let's say that. Does that make sense? On our interval. Then we say it's a minimum. It's a maximum if when we plug c into the function, there's no other point that's higher than that on our interval. Okay, that's how we would define an extremum. So now we got to get a little more specific. If we're going to talk about local or we usually call them relative. Sometimes people call them local extrema. What does that mean? Well, that's just saying that we're going to look at only one specific interval, but there might be other places outside of that interval where you could have higher or lower values. Okay, so if there's an open interval containing c on which f of c is a maximum, then f of c is called a relative or local maximum. So this is important. Topologically, that just means it's a peak. If you looked at the graph, it would look like a peak on the graph. What's a relative minimum? Relative minimum would be on some open interval containing c. If f of c is a minimum, then topologically we would say that that's a relative minimum and it's a valley. It's going to look like the bottom of a valley if we look at the graph. Okay, so that's really important to think about that stuff. Just some reminders. An open interval from A to B means what? Not including the endpoints. A closed interval is exactly the same as the open interval, but what are we doing? Yeah, we're just including the endpoints, right? So the closed interval from A to B equals the open interval from A to B plus A plus B, plus those endpoints, right? Okay. So what about an absolute extremum? What's the difference? Well, an absolute extremum, we're saying if I give you some specific interval, now I just want to know what is the highest place on that interval and what is the lowest place on that interval. It doesn't have to be a peak and it doesn't have to be a valley. It could be an endpoint or something also, okay? And then a global extremum just means that if I take the natural domain of the function, so all the x values that could possibly work on that function, there is one peak that is the highest. The highest peak would be the global maximum, and the lowest valley would be the global minimum. Okay? So a lot of vocabulary, but really the stuff we're going to focus on primarily are going to be relative extrema and absolute extrema. Okay? Relative extrema, remember that means peaks or valleys. Absolute extrema just means on some interval, the highest place an ant could stand on the function and the lowest place the ant could stand on the function. So if we wanted to label some stuff, if I take this function right here, this oscillating function, there are a whole bunch of relative maxima. All the peaks are relative maxima. Any place where an ant could stand on this function and say, I'm higher than all of the territory right around me, that's a peak, right? That's a maximum. This is a relative maximum, even though there's a much higher one that he can see in the distance, right? But those are all peaks, so those are all relative maxima. These would all be relative minima. The bottom of every valley that we see is a relative minimum. What's the absolute maximum on this? Let's say on the entire real line, all values of x are fair game. Then there is an absolute maximum right there. That's the highest place that ant could stand. And we could call that a global maximum because there's no other place that could possibly be higher. What I probably should have done here is I probably should have said something like an absolute maximum on, let's say, something like this. Like on -1 to, I don't know, to 5 or something. And let's just say that that's -1 and that's 5. Between -1 and 5, there is an absolute maximum right there. Okay? Between -1 and 5, there's a shared relative minimum because there's two valleys that are equally low, the lowest that an ant could possibly go, right? What about a global maximum? Yeah, global maximum would mean on all possible values, and that's a global maximum. It looks like there is no global minimum because this thing just goes down forever, the way it's drawn at least. Okay, does that make sense? You kind of get an idea about the vocabulary? Okay.
Maximum or global maximum have a value?
Say it again.
Do the two maximums have a value?
Well, yeah, the maximum would be whatever the y value is at that point. We'd say that's the global maximum. A lot of times we're more interested in where it occurs than what the value is, though. Yep, question.
So I missed it, but is the difference between the maximum and the global is the entire graph, and the absolute has to be given x?
Yeah, right. So absolute means we're going to specify some interval. Global means in the entire universe of values that could work. Say it again. Relative is just any peak or valley. Relative maximum would be any peak. Relative minimum would be any valley. Okay. I don't know what that's for. Oh, that's just I think that's just from the last one. I mean, we can skip that. That's not a big deal. Okay, so again, this just reiterates, just kind of for your notes, essentially a relative maximum is always a peak and a relative minimum is always a valley. Okay, and we already talked about that. Okay, so this brings us to one of the big existence theorems, right? These are really big in calculus, these existence theorems. We've seen like one or two of these so far, but these are the ones that say if you meet these criteria, then something exists. Okay, what's this? And a lot of times in calculus, we would just call this EVT, is the extreme value theorem. So if f is continuous on a closed interval from a to b, then f has both an absolute minimum and an absolute maximum on that interval. Okay, let's make sense of that. Think what that's saying. If I've got some interval from a to b, all we have to know is if the function is continuous on that closed interval, so that means I can put my pen on the board at x equals a and draw a smooth curve. Well, it doesn't even have to be smooth. I just have to draw some function without picking my pen off the board until I get to b, and when I get to b, I pick it up. If that's it, that's the only criterion that we need, and then that tells us that that function has to have both an absolute minimum and an absolute maximum. There's no way it couldn't, right? Like, let's think about that. If I put my pen down there and I draw some function like that, well, then there has to be some place on that interval, because I didn't pick my pen up, where the ant would be at the highest place, right? And that's going to be our absolute maximum. Where is it in this case? I mean, right there, isn't it? Right, that's our absolute maximum. right there. Where's the absolute minimum? Well, the lowest place, right there. Can anybody think of a trick where maybe I wouldn't have one? If it's a straight line, what about the straight line? If it's horizontal? Okay, so even then, now that's the case I was hoping somebody would bring up. Even then, if I did something like that, it still like every point is a shared maximum and every point is a shared minimum. The ant is always standing at the highest possible point and the lowest possible point. You got another one?
Well, it wouldn't be a vertical line because it's not continuous.
Right, you couldn't do a vertical line because you could never get from A to B. Exactly. See what I'm saying? Yeah. That's kind of a boring one. I mean, we're not going to really have to spend a lot of time thinking about that one because it's a pretty boring function. But for every other function that's not super boring like that, there's always going to be, a place that's the highest and a place that's the lowest. And it could be a tie. I might have multiple peaks that are at the same height. That's okay. It's a shared absolute maximum then. Okay? So examples of relative extrema. Just threw some in from Desmos. So here's one. Like if we take this function f of x, that's what that function looks like, and there's a peak, right? Everybody agree that's where the ant would be at the highest place on that function, at least, in his immediate surroundings, okay? What do you notice about the tangent line at that point? What's the slope of the curve at that peak? It's 0, isn't it? Yeah, okay, that's interesting. Here's another one, sine function. Notice that has a flat, horizontal tangent line at that relative maximum and at that relative minimum, right? How about this one? F of x equals the absolute value of x. Wouldn't you agree that that's a relative minimum right there? Okay, what can you tell me about the derivative at that point? It what? How come? You're right. You're right. Why is it undefined there? Yeah, because it's a sharp corner, right? Remember we said there were some places where derivatives don't exist. They don't exist if there's a break in the function, if it's a sharp corner, or if it's an infinite, like if it's an asymptote, then it wouldn't exist, or if it's a vertical tangent line, right? There's some places where derivatives just don't exist. So that doesn't exist there because there's a sharp corner. Interesting, okay? So we found two different types. We could generalize this a little bit. Peaks or valleys that are smooth and rounded are always going to be peaks and valleys that occur at places where the derivative has a horizontal tangent. The function does have a tangent there, doesn't it, right? Peaks or valleys that are sharp are always going to be places where the derivative is undefined because it's a sharp corner. Okay, that's going to end up being really important. So again, for your notes, there's different types here. We could have undefined derivatives give us sharp peaks. Smooth, rounded peaks are where the derivative is equal to 0. Okay? And same thing for valleys. We could get, smooth valleys where we get a horizontal tangent line, sharp valleys where we get an undefined derivative. Okay, so then that brings us to something really important. And you got to make sure you don't generalize too much on this, or you could make mistakes. This is a true statement. Relative extrema occur only at critical numbers, and we're going to define critical numbers as places where the derivative is either equal to 0 or it's undefined. Doesn't that make sense logically? In order to have a peak or a valley, it has to either be a smooth peak or valley or a sharp peak or valley. There's no other kinds of valleys you could have other than smooth, rounded ones or sharp ones, right? Make sense? So therefore, every extremum has to occur at one of these kinds of places where the derivative is equal to 0, where it's got a horizontal tangent, which makes it a smooth either peak or valley, or the derivative is undefined, which makes it sharp. Okay? Give me thumbs on that. Does that make sense? Okay? And there's just some examples, right? Okay, but not all critical numbers are going to turn out to be extrema. There could be places where the derivative is equal to 0 or where it's undefined that don't correspond to peaks and valleys. Here are some examples. An inflection point like this. This isn't a great drawing, but imagine you have a function that comes up, levels out, and then keeps going up, like an x cubed function, for example. Okay, well, that is a horizontal tangent. The derivative is equal to 0 there, and yet it's not a peak or a valley, right? You could have places where the derivative is undefined, like a vertical tangent line. Again, that's not a peak or a valley, though, right? So not all critical numbers are necessarily going to yield extrema. However, every extremum would have to occur at a critical number. Okay, give me a 1 to 5 on your level of comprehension of that statement, because that's really important, right? Does that make sense? All extrema must occur at critical numbers, but not all critical numbers correspond to extrema. There could be some false alarms. There could be some relative, or there could be some critical numbers that don't give us extrema. Okay? Okay, and they're just some examples of some specific functions, right? I guess I did pick some. So like there's a good one, right? There's a cubic function where we have, there's a critical number because it's a place where the derivative is equal to 0, but it's not an extremum. And here's a function where we have a vertical tangent. So there's that's a critical number. X equals 1 is a critical number because the derivative is undefined there, but again, it's not an extremum. Okay, so this is kind of this is sort of an obscure one that I wanted to throw out here because it makes sense. Fermat's theorem. If f has a relative extremum at c, so c is some value of x, it has a relative extremum there, and if the function is differentiable at c, then what does that tell you about the derivative? So what's the first part of that mean? Just describe that in simpler terms. If f has a relative extremum at c, what's that mean? If you were explaining this to somebody who wasn't in calculus yet, what would you? Peak or a valley. So there's a peak or a valley at c. Good. And f is differentiable at c. What's that mean? You can take the derivative at c. The derivative exists. Okay? So then put those, what's that mean? No, I think you are. What did you say? Has to be 0. Yeah. Because what kind of an extremum would that have to be in that case? Sharp or rounded? Have to be a rounded one, right? A smooth one, right? It can't be a sharp one or it wouldn't be differentiable, right?
Oh my goodness.
So look, you figured it out. Okay, it has to be 0. Good. Okay, so quick vocabulary summary. If we kind of just informal language, relative extrema are peaks and valleys. Absolute extrema are the maximum values and or minimum values on some specific interval. Global extrema are the maximum values or minimum values on the entire domain of the function. Okay? Okay, so now, I got some questions for you. In which of the following cases do absolute extrema exist? And what are they? So look at this first example. Give me thumbs on this. Do we have an absolute maximum on this first example? What's that mean? Somebody summarize that. What's that mean in terms of an ant? Do we have an absolute maximum on the interval from -1 to 2? What's that mean in terms of the ant, though? The ant could do what? Okay, he could stand on one place and unequivocally say, I'm at the highest place on that interval. True or false? Yeah, where does it occur? Yeah, at that endpoint right there, doesn't it? So that is an absolute maximum. Yes? Is there an absolute minimum? Where? Right there. Yeah, that's an absolute minimum. Because again, the ant could stand there and state correctly that he's on the lowest place on the function on that interval, right? Okay, how about case B? Is there a maximum? No. How come? He can't stand there, but couldn't he just stand on the point next to it? Oh, what's that? He can keep getting closer. It goes back to that door example, right? Remember the door example? If I keep cutting my distance to the door in half every second, mathematically I never stop moving. I'm always getting closer. And how many points are always between me and the door? Infinite number, right? So, yeah, so there is no place the ant could ever stand there and say he's at the highest point because that end point is open. Anybody get that? So there is no absolute maximum. How about a minimum? Yeah, there is one. How about this guy? What's different here? There's no minimum because we have a hole in the function right there. Okay? So this is a topic, I'll just weigh in on this. So is there a relative maximum at x equals -1? Is there a relative maximum? You know, for that matter, can a relative extremum even exist at an endpoint? So the best answer is it depends, honestly. I can't believe there are still things like this where people feel differently about it, and it's different textbooks will literally say different things. And it's one of those things where you have to just kind of establish a convention and stick with it. Almost every undergraduate text is going to say no, because in order for a point to be an extremum, we must be able to approach it from both sides.
So would
Okay.
that mean that the maximum extremum would not be one?
It wouldn't be a relative extremum. By that standard, it'd be an absolute extremum, but it wouldn't be a relative extremum, because a relative extremum you'd have to be able to approach from both sides. That's what almost every textbook says. I tend to disagree with that, honestly. I think there are some other compelling arguments you could make where you could say, well, it doesn't really matter. If you can only approach a point from one side, that should be enough. That seems consistent with the idea of a one-sided limit to me, and it just seems like that makes more sense. But we'll just go ahead and adopt this convention where we'll say, no, those aren't relative extrema because we can't approach them from both sides. It's not fully a peak if you can't walk up both sides of the peak, I guess. Okay? So, what did I want to do on this one? Okay. Does this function have absolute extreme values on the open interval from A to B? Has a minimum. Okay, but it doesn't have a maximum, and it's not consistent with the extreme value theorem, is it? What about this does not apply to the extreme value theorem? There was very specific wording on the extreme value theorem. It's continuous, but it has to be a closed interval, right? I can't put my pen on the board at A and take it off at B because those points aren't included. So extreme value theorem always implies a closed interval. Okay. All right. Okay, does this function have an an absolute minimum from A to B? From A to B? It still has a minimum, doesn't it? Now, the extreme value theorem wouldn't apply, but it still does have a minimum, doesn't it? Right? Right there, doesn't it? Agreed? Okay. Does it have an absolute maximum? No. Okay. How could, well, I'm not going to mess with that. Never mind. Does it have an extreme, does that function have an extreme or an absolute minimum? No. Absolute maximum? Yes. Okay. How about that one? Neither.
How does it have an absolute maximum?
How did this last one have an absolute maximum? Well, we're assuming it doesn't go up, it's a really sharp point, but it does have a peak. Were you thinking it was asymptotic or something?
Well, no, like sharp peak, it's still a maximum, even though you can't take the derivative?
Yeah, it doesn't matter. Absolute, for an absolute extremum, you doesn't have to be, that's for a relative extremum, right? Does that make sense? Okay. I mean, it still could be a relative extremum, but just be a place where the derivative's undefined, though, too, right? Okay. No on that one, neither one. Okay. Identify the graph of a function, A, B, C, or D, that has a local minimum value where f prime of A is equal to 0. A, B, C, or D. Has a local minimum value where f prime of A equals 0. Two of those look pretty similar, but one of them's supposed to be a sharp corner, just FYI. So it's B, isn't it? Yeah. This one, you see it comes down and then it goes from linear to a curve. So it'd be B, because that's where I have a horizontal tangent at A. Agreed? Okay. Identify the graph A, B, C, or D has a local minimum value at B where f prime of B is undefined. A, right? Sharp, it's a valley with a sharp peak, or sharp, it's a sharp valley at B. Agreed? Okay. Identify the points on the interval from A to B at which local and absolute extreme values occur. So where would all of the local minima occur? X equals did we say A? What did we say about local or relative extreme at endpoints? You have to be from both sides. So we're not including those, right? I think our textbook, hope our textbook's that way. I thought it was. If it's not, we'll switch. So then what would be the local minimum points? Q, I like. S. What, you guys tell me, would T be one? The derivative is 0 at T, but is it a minimum or a maximum? No, it's not. And okay, how could you tell? If an ant were standing at T, in order for it to be a relative maximum, if the ant walked to the right or the left, he'd have to be going down, right? Does that make sense? If it were a minimum, same thing. If it was a minimum, he'd have to walk left or right and go up. That's not the case here. If he walks left, he goes down, right, he goes up. So it can't be either one, right? Relative to the terrain right around him, that is not the highest point. Locally speaking, it's not the highest point or the lowest point. So only those two. Where would local maximum values occur? P, R, and I guess that's it, right? Absolute minimum values occur at what? A. That's it. Right? That is the lowest point on the function. Absolute maximum values occur where? Looks like P and B are equal, doesn't it? I think that's the idea, is those are supposed to be equal. Okay, we'll say they're equal. Okay, location of absolute extrema. So where could absolute extrema exist? I've got some interval. What are the only kinds of places where an absolute maximum or minimum could occur then? Okay, highest or lowest points, but where could those be? Not anywhere. I mean, I want to know more specifically. I mean, I guess they could be anywhere in the interval, but if an ant were at a local, at an absolute maximum, what are the only two kinds of places he could be standing? The highest point on some interval. Describe the topology there. What are the only two kinds of places he could be standing? Okay, there you go. It could be a peak or it might be an endpoint, right? Those are the only places where it could be, right? An absolute minimum could only occur at the bottom of a valley or at an endpoint on the interval, right? So we get absolute extrema must occur either at endpoints or at critical points, right? I mean, they'd have to be at critical points because all of the extrema would occur at critical points. Agreed? Peaks and valleys would all have to occur at critical numbers. Critical, when we say, and this is another thing, books sometimes get a little bit lazy with this. A critical number are the x values. Those are the input values where the derivative equals 0 or it's undefined, right? All relative extrema have to occur at x values that are critical numbers. A critical point would just be the places on the curve where that's happening, right? So critical points are places on a graph where the derivative is 0 or it's undefined. Okay? So now let's come up with a strategy. Now we're going to actually get into doing some problems here. Let's come up with a strategy for finding absolute extrema on a closed interval. Okay, well, what could we do? Say it again. Okay, but we don't have a graph available to us this time. All we have is a function. Okay, so we want to find all the critical numbers, all the places where the derivative is 0 or where the derivative is undefined. There you go. Okay, so the first thing is find all the critical numbers. Okay. What else? Where else could we possibly get in the endpoints? And that's it, right? All we have to do is find the critical numbers of our function in our interval and evaluate the function at each critical number. Evaluate the function at each endpoint, and the least of those values is guaranteed to be the absolute minimum. The greatest of those values is guaranteed to be the absolute maximum. There's our strategy, right? Just find the critical numbers in the endpoints and evaluate the function at all those places and see who the winners are, biggest and the smallest. Okay, so let's try an example. How about one like this? So we're looking at the function at this polynomial function on the interval from -1 to 0. So we got to take a derivative, yep. First step would be to take a derivative. So what's our derivative? Okay. Good, so there's our derivative. So give me thumbs. Are there going to be any places where the derivative is undefined? No. Polynomials are defined everywhere, aren't they? There's no reason that they wouldn't be. What kinds of things would, where would you look on a function? What kinds of things would cause it to be undefined? I mean, okay, you could have something weird like an absolute value. Barring any weird absolute values, what other kinds of things would we look for? Square roots. If we have any even root, right? I can't take an even root of a negative number. Okay, that's something. What else? What is it? I think you might be on the right track. So there's another one that's the most common one. Any place where an x value would cause us to do what? If I've got some rational functions where I have x's in denominators, let's say. Yeah, any place where I'd get a 0 in a denominator. I can never divide by 0. So normally those would be the kinds of places where we would find that a function's undefined, derivative's undefined, right? Any place where we're forced to divide by 0 or take an even root of a negative number, or some odd cases where we've got piecewise functions like absolute value functions and the derivatives don't agree, okay, from the left and the right. We don't have to worry about that here. How about places where it equals 0 though? Maybe, right? We might have places where the derivative equals 0. So to find out, we would just set it equal to 0 and solve that equation. So go. What do we do? Yes, divide everything by 3. Good idea. So we get 3x squared minus 2x minus 1 equals 0. How are we going to, I want you to be efficient about this. Let's find the easiest way to solve this quadratic equation. What would it be? Yeah, but we don't do slip and slide, right? Slip and slide. We do split and group. right? You guys don't want to do slip and slide is terrible. We don't want to do slip and slide.
I thought we always did.
No, slip and slide. Remember, I scolded you for this slip and slide. I reminded you about it, but I told you, okay, I'll tell you, remind you, but don't do it, right? What we do instead, let's review this. This is important. So slip and slide is a trick. It's not an algebraically rigorous process. You can't go from step to step and have them be algebraically equivalent. You have to do it as kind of side work. It's kind of goofy. We don't want to do that. We want to do something that's algebraic. It's the same thinking, by the way. You have to find the same magic numbers that you would in slip and slide, so just do it this way. We want to find magic numbers that multiply to the product of the outer coefficients. If we've got a quadratic trinomial, that's what we're dealing with, right? So our magic numbers would have to multiply, call them m and n, they'd have to multiply to -3, right? The product of the outer coefficients. And they have to add to the middle coefficient. Well, what magic numbers do that? Multiply to -3 and add to -2. -3 and 1. Okay, so then we get, those are our magic numbers. So once we find those, that's how we're going to split the middle term, and then we'll just factor by grouping, because now we'll have 4 terms instead of 3. If you can find, remember this stuff? If you can find the magic numbers, factoring by grouping is 100% guaranteed to work. So we split this up, and we're going to split up the -2x into what? -3x plus 1x. If you have opposite signs, this is just a little, this is not a big deal, but I always want to put the -1 first. So you put remember the circled plus sign that splits the two groups? That way you can put the plus sign in the middle, it's already there. So we'll split this into a -3x and a plus x, and then we'll circle that because that's our middle sign. These guys stay the same. And then we just factor by grouping, and it's easy, right? So what do I factor out of the first group? 3x, there you go. I take out a 3x. What's my leftover from the first group? Okay, remember with factoring by grouping, what do we do next?
Factor to get the term side.
Yeah, we have to have the same binomial, right? So we just start with the binomial. You always start with the binomial because you know that has to be there. And then answer the question, what goes out front? 1. If we factor out our common binomial factor, what's left behind? There you go. Right? Okay, so what are my solutions?
1/3, -1/3.
Okay, so we get x equals 1 or, whoops, x equals -1/3. So those are places, now remember, we just did a bunch of algebra, but what we were trying to do is find where the derivative equals 0. So on our closed interval from -1 to 0, which of those is important? Yeah, the -1/3. The 1 is outside, that's outside of our interval, right? And if it were an endpoint, we wouldn't care anyway. Does our go from -1? Yeah, it does. Even if that were a -1, we don't care because it's an endpoint anyway. We're already going to test it. Does that make sense? But this is a critical number. This is what we would call an interior critical number, right? Everybody get that? Why is it interior? Yeah, because it's between the endpoints and it's a critical number. So what are the only places where absolute extrema could occur on our function then? -1/3 or you guys told me earlier that they could occur at critical numbers or endpoints, right?
Oh, -1/3, 0.
-1/3, 0, or -1. Yeah, those are the only places we'd need to check. We have 1 minute? Yeah. Okay, I'm going to show you the greatest gift I can give you. I'm going to show you my patented tables, calculus tables tomorrow. And this is one you're going to want to take to college with you. This is a useful one.
Our late balance.